Hello, I'm Joe French, and I'm coming to you from my classroom in Mount Pleasant, Utah. And this is topic 2.5, applying the power rule. And we're going to look at some examples of how the power rule might be used. Now that we have this awesome tool, hopefully it will make our work in finding derivatives much, much easier. Here we're trying to find the limit as h approaches 0 of this expression. But when h approaches 0, that sounds an awful lot like our difference quotient or definition of the derivative, right? Approaches 0 of f of x plus h minus f of x over h. And we know that that limit is simply the derivative of x. So if we know what function we're working with here, which is indicated back here at the end of our difference quotient, then all we need to do is apply the power rule because these are all power functions. So if I look here, I can look at this 2x plus h squared minus 3x plus h plus 4, and then I'm subtracting f of x. So if I put a subtraction sign and then a parentheses so that I can see what I'm actually subtracting, which means I factor out a negative from the last three terms, so I get 2x squared minus 3x plus 4, all over h, and we're looking for the limit as h goes to 0, or approaches 0. Now, this last piece in the parentheses is my f of x. So this question is actually asking me, what is the derivative with respect to x of 2x squared minus 3x plus 4? And that means we can apply the power rule. The derivative of 2x squared using the power rule is going to be 4x. Bring down the exponent, multiply it times the 2, 4x, leaving me x to the first, 2 minus 1. And the derivative of negative 3x, well, that's the derivative of a line whose slope is negative 3. And then we have a 4. The derivative of 4, y equals 4, is a horizontal line at y equals 4. The slope there, our rate of change, it's not changing. It's not going up. It's not going down. So that would just be 0. So my derivative, or the answer to this limit question, is just 4x minus 3, or plus, no, minus 3. Sorry about that. That should be a minus. Let's look at another example. What is the value? Oh, look, it's another limit as h approaches 0, which means that we're looking probably at another difference quotient, only now we've got numbers instead of x's. So the question is, what do those numbers, how do they fit into an f of x equation? So if h goes to 0 here, this would be the same as 27 to the 1/3 minus 3 over 0, which is 0 over 0. This is my limit, which is undefined, right? But 0 over 0 is undetermined, not undefined. So we need to figure out what's going on here. So we have this number being raised to the 3rd power, which happens to equal the number we're subtracting. Well, the number that's being raised to the 3rd power, we could write in a more general instance as some number being raised to the 3rd power. And then we're looking at a specific number when x equals 27. So my f of x will be this expression x to the 1/3. And then I am trying to find what the value of my derivative is when x is 27, based on the expression given to me. So let's apply the power rule to f of x equals x to the 1/3. Remember, f prime of x. The power rule says to bring down the exponent, the 1/3, then raise x to 1/3 minus 1, which would be 1/3 x to the negative 2/3, which could also be written as 1/3x to the positive 2/3. Remember, to change a negative to a positive, we simply move the x to either the numerator or denominator, changing its position. So there's my expression for my derivative of f. Now, what we want to do is evaluate our derivative f when x is 27. So I'm looking for 1/3 times 27 to the 2/3. I like to think of that as 1/3 times 27 to the 1/3 squared. Remember how I can break out my fractions, and raising an exponent to an exponent is the same as multiplying the two exponents together. So 27 to the 1/3, that's the cube root of 27, which is 3. So this is 1/3 times the cube root of 27, or 3 squared. Well, 3 squared is 9 times 3 is 27. So my derivative at 27 for this function x to the 1/3 is 1/27. Let's take a look at one more. Here I have a function, piecewise function, g of x, where for x less than 2, I'm looking at the line 14 minus 6x. For x greater than or equal to 2, I'm looking at the line 5x plus 2. So to find the derivative at 2, g prime of 2, I need to think about, is the function differentiable at x equals 2? For a function to be differentiable, that would mean that, first of all, it's continuous. So is this function continuous? First, I'll look at the left and right hand limits. As x approaches 2 from the left, this graph gets closer and closer to 14 minus 6 times 2, which would be 14 minus 12, or 2. Then I'll take a look at the limit as x approaches 2 from the right, using our of g of x, use the second equation, because we're using values like 2.01, 2.001, and that would be 5 times 2 plus 2, which is 12. So here, since our values don't even connect, this graph is discontinuous, and g prime of 2 would be non-existent. We can also tell that the graph isn't differentiable because even if they had connected, if we looked at how they're connecting, here we have a sharply negative slope, -6, and here we have a sharply positive slope, 5x. So we're looking at a graph that, even if it connected, comes together at a sharp corner, which would make it non-differentiable. So g prime of 2 does not exist. And that's the end of our example.